Welcome to part 4 of taking the mystery out of pi. We have here a beautiful picture of Crater Lake in Oregon. It was formed many years ago when a volcano collapsed. And what we want to do here is we want to estimate what the distance is around this lake. And the first thing that I notice here is that this lake is pretty close to being circular. It's pretty close to being a circle. We can approximate it with this circle here. And this circle turns out to have a diameter of 5 miles. So the question is, what would be the distance around this lake? What would be the circumference of this circle? So pause and ponder on that for a moment. Okay, remember, the diameter is that distance across the circle. It's the distance that Mac would just die to run across. Remember that? And the circumference is the distance around the circle, which is always a little bit more than 3 times bigger than the diameter. And in this case, it's a little bit more than 3 times bigger than our diameter of 5 miles. It's exactly equal to the 5 miles times pi, or 5 pi miles. But what does that tell us about our original question, the distance around the lake? Well, remember, the lake is not an exact circle. It's just kind of close to being a circle. So all we can really say here is that the distance around the lake is about equal to 5 pi miles, which in turn is about equal to 15.7 miles. Okay, so for this question, we have a bicycle wheel with a nasty old paint blob on the bottom of it. And every time that paint blob makes contact with the ground, it leaves a mark behind. So this particular bike wheel has a radius of 1 foot. If you don't know what a radius is, a radius for a circle is the distance from the center of the circle to the outside of the circle. And it's actually the distance from the center of the circle to any point on the outside of the circle. It's always the same. It's always going to be 1 foot if we go from the center to any part on the outside of the circle. The way I like to think of it is that you kind of like have the sun in the middle, and the sun's giving off these rays, and the radius is the distance that ray travels from the center, from where the sun is, to the outside of the circle. It's a nice way to remember it. So the question here is, if we rotate this bike wheel, if we move it along the ground like this, what is the distance between the 2 paint blobs that we get? And keep in mind that the entire circumference of the bike wheel is making contact with the ground as we rotate it from this point over here to this point over here. So again, the question is, we have a radius of 1 foot. That's the distance from the center to the outside of the circle. And what we want to know is what is the distance between these 2 paint blobs. So pause and ponder on that. Okay, I kind of hinted at this before. Remember that the entire circumference of this bike wheel is making contact with the ground. So when we roll this wheel along the ground, the distance that it's going to travel from one paint blob to the other is just equal to its circumference. Think about that a little bit on your own if you need to. It may not be completely obvious, but this distance from the left to the right is exactly equal to the circumference of the bike wheel. Now the other thing that's a little tricky about this problem is that I gave you the radius, right? The distance from the center to the outside of the circle. And I'm basically asking you to find the circumference of the circle, the distance between the paint blobs. But I never really showed you how to do that before, right? I showed you how to go from the diameter to the circumference, right? We talked about the circumference being a little more than 3 times the diameter. I never showed you how to do it from the radius. Do you have any ideas how you can get from the radius to the circumference of the circle? Think about that a little bit on your own first. It's time to pause and ponder. Okay, in case you haven't figured it out yet, let me give you a hint. Is there a way that we can figure out the diameter of the circle from the radius? Because if there is, we should be done, right? Because we know how to get from the diameter of a circle to the circumference. So is there a way that we can figure out the diameter or the distance across this circle? Pause and ponder on that. Okay, remember how I said before that the radius is the distance from the center of the circle to any point on the circle. It's like a ray going from the center to the outside of the circle. So what I notice here is I've drawn a radius that goes from the center and it just goes straight across to the right. And that radius is 1 foot. But what I can also do is I can draw another radius that goes from the center straight across to the left, and that's also going to be 1 foot. And guess what happens when I put those two radii together? I get the diameter, of course, which is the distance that's straight across the circle. So that means that our diameter is going to be 1 + 1, or 2 feet. The first one for the left radius, the second one for the right radius. Okay, so now it should be pretty easy. We have a diameter of 2 feet, and that means that the distance between the paint blobs, which is the same as the circumference of the circle, is going to be roughly 3 times 2 feet. It's going to be roughly 3 times bigger. It's going to be exactly pi times bigger than the diameter. So it's going to be roughly, not roughly, it's going to be exactly pi times 2 feet, or 2 pi feet. Now this is approximately equal to 2 times 3.14, our first approximation for pi, which in turn is equal to 6.28 feet. We can also say that this is approximately equal to 2 times our other approximation for pi, 22/7, and that gives us 6 2/7 feet, which is also close to 6.28 feet. So we just figured out a specific case. We figured out the circumference of a circle whose radius is 1 foot. But how do we get the circumference in general if we're given the radius? The radius could be anything. It could be an inch, it could be a mile, it could be a parsec, it could be anything. What I'm looking for here is a general formula that relates the radius to the circumference. Now we already have a general formula that relates the diameter to the circumference, right? We have that the circumference is equal to pi, a little more than 3, times the diameter. Often this formula is abbreviated as circumference is equal to pi d, right? Where d is just an abbreviation for the diameter. So I'm looking for a similar type of relationship, but not between the diameter and the circumference, but between the radius and the circumference. Can you come up with a general relationship between the radius and the circumference? Pause and ponder on that. Okay, let's start with what we know. What we know is that the circumference is pi times bigger than the diameter. Now, if there's some way that we can write the diameter in terms of the radius, we're done. Because then we have radius stuff over here times a bunch of stuff is equal to the circumference, and we're done. Okay, remember from before that the diameter is equal to the right radius plus the left side radius, which of course means that it's equal to twice the radius, the left plus the right side radius. Remember before we had a radius of 1 foot? So if you had a radius of 1 foot on the left and a radius of 1 foot on the right, the diameter then was just equal to the 1 + 1, or the 1 times 2. So the diameter is always equal to 2 times the radius. So actually we're done at this point, right? Because we're saying that the circumference is equal to pi times 2 times the radius. But this isn't usually the way people express it. It's just tradition, I guess. The way it's usually written is that the circumference is equal to 2 pi r. And you can see where each one of these pieces come from, right? The 2 comes over here. We're just reordering things. The pi goes from here. And the radius we just abbreviate with the letter r. So it's a very common formula. You're going to see it a lot. The circumference is equal to 2 pi r, which basically means that it's about 6 times bigger than the radius. The circumference is about 6 times bigger than the radius. Okay, for this problem, we're going to step way back out into outer space, and we're going to look down on the Earth. And we're going to make an assumption here. We're going to assume that the Earth is a perfect sphere. Right? We're going to ignore the fact that there are mountains and valleys and humps and bumps and lumps on the Earth. We're going to ignore all that. We're going to pretend it's a perfectly smooth sphere. And we're further going to assume that it has a diameter of 7,901 miles. That means that if you were to start digging on one side of the Earth and you were to dig a hole right through the center of the Earth and come out on the other end, that it would be 7,901 miles long. That's how long that hole would be, to go right through the surface of the Earth. Now, in this problem, there is a belt that goes around the Earth. And the belt is going right around the center of the Earth. It's separating the northern hemisphere up here from the southern hemisphere down here. The belt's going right along the equator. It's perfectly snug with the Earth. But there's a problem with this problem. And the problem is that there are a bunch of angry ants. Because you see, the belt's not a big deal for us. We can just walk over it. It's just like kind of flush with the Earth. But to a little tiny ant, that belt is like this huge obstacle. It's like this big mountain that it's got to go over. So these ants are really angry that this belt is just flush with the Earth like this. Now you may be wondering, why are we worried about what a bunch of ants think, right? They're just little insignificant insect creatures. But let me remind you about a few things here. First of all, did you know that if we take all of the ants on the Earth and we put them on a scale, and we take all of the people on the Earth and we put them on another scale, did you know that they're going to weigh about the same amount? That's an awful lot of ants. And did you further know that ants are very, very strong? For ounce, they're 20 times stronger than we are. If we were as strong as ants, when you compare it to our weight, we wouldn't need to drive in cars. We could just be lifting them on our back, and the cars could be driving us. It would be crazy. So if these ants could organize themselves, it would be a pretty scary world out there, because they'd be 20 times as strong as us. So at any rate, just something to think about. At any rate, these ants are really angry in this problem, and what they want is this belt to be lifted 1 foot off of the surface of the Earth all the way around. You can see this figure here. Obviously, I've exaggerated, this 1 foot so you can see it. But they want this belt to be lifted off of the surface of the Earth 1 foot all the way around. Okay? And the problem that I want you to consider is obviously the belt needs to, we need to make the belt longer, right, to be able to make it 1 foot above the Earth's surface rather than just flush with the Earth's surface. So the question I have for you is, how much longer do we need to make the belt in order to accomplish this? Time to pause and ponder. Okay, this is definitely the hardest question I've asked you so far. So I'm going to break this down into a couple sizable pieces in case you didn't get the answer right away. So let's look at the following diagram here. This inner circle represents the Earth. It represents the equator of the Earth. If we were looking down on the equator, that equator that goes around the center of the Earth is a perfect circle. And if we look down on it, remember, it's 7,901 miles from one side to the other. So this circle, therefore, has a diameter of 7,901 miles. Think about that a little bit if you need to. We're kind of going from like a three-dimensional picture of the Earth to like a two-dimensional picture where we're just focusing on the equator. Now, this outer circle, and you may have guessed it, is the belt. It's the enlarged belt. It's the larger belt that the ants are demanding. And this belt is 1 foot above the Earth all the way around, right? So it's going to be 1 foot out from this equator all the way around it. So we have one, I'm calling it an exaggerated foot because a foot would really be so small you wouldn't even be able to see it, right? If this were 7,901 miles, you wouldn't even be able to see the foot. So I've exaggerated it here so that you can see what I'm talking about. So we have one exaggerated foot on this side, and it actually goes all the way around the circle as this one exaggerated foot. And then we have another exaggerated foot, on this side. And it continues to be 1 foot, more distant from the center all the way around. So this is the larger belt. So the Earth is the inner blue circle, and this extended belt that the ants are demanding is the larger circle on the outside. So the question I have for you, the first sub-question here, is what is the increase in diameter when we compare the Earth, when we compare this equator, which would represent the snug belt that's just hugging the Earth, versus this new larger belt? How much has the diameter increased from the snug belt to the enlarged belt? So pause and ponder on that for a while. Okay, this basically comes down to how much larger is the diameter of the enlarged belt than the diameter of the snug belt that just hugs the Earth all the way around the equator. So to do this, we're going to try to figure out what the diameter is of the enlarged belt. So the first thing I notice is that we have 1 foot here on the left, and then we go 7,901 miles all the way across the Earth through the center of the Earth. And that 7,901 miles is common to both the larger diameter and the smaller diameter, right? Because they both have to encircle the Earth. And then, of course, we have 1 foot here on the right. So when we put this 1 foot on the right together with the 1 foot on the left, you guessed it, we have 2 extra feet here, plus the 7,901 miles. So hopefully it's pretty obvious to you that the diameter of the enlarged belt down here is 2 feet bigger than the diameter of the Earth, or the diameter of the snug belt that's hugging the Earth all the way around, because the 7,901 miles is common to both and cancels out. So the increase in the diameter is 2 feet. But that begs the question, when we increase the diameter by 2 feet, how much do we increase the circumference by? So I want you to pause and ponder on that for a moment. Okay, so this is a little twist on something I've been talking about a lot up till now. So in case you didn't get it, let me remind you, let me give you a little hint here. Remember when we were talking before and Mac was running around in circles? The question here is, if the diameter increases by 1 foot, how much does the circumference increase by? Remember, Mac kept running around these bigger and bigger circles, and each time the diameter would increase by 1 foot? How much extra did he have to run around that pie dish each time the diameter increased by 1 foot? Pause and ponder on that for a moment. Okay, hopefully you remember that each time the diameter increases by 1 foot, the circumference increases a little bit more than 3 feet. It increases exactly pi feet. But that's still not quite our question here, right? Because in this problem, the diameter is increasing by 2 feet. So when the diameter increases by 2 feet, how much do you think the circumference increases by then? Pause and ponder on that for a moment. Okay, in this case, the diameter is increasing twice as much as before. It's 2 feet instead of 1 foot. And because the diameter is increasing twice as much, the circumference also increases twice as much. So instead of pi feet, it's increasing by 2 pi feet. The other way to look at this is that every time you have an increase in diameter of 1 foot, you have an increase in circumference of pi feet. So if the diameter is increasing by 2 feet, then the circumference is going to increase by pi plus pi feet for each foot of increase in the diameter. So this is actually pretty amazing, right? We're talking about the entire Earth here. It's so huge. And just to lift the belt 1 foot off the surface of the earth all the way around. You would think it would take miles and miles of belt to do that, but no. It only takes 2 pi feet. It only takes a little bit more than 6 feet of extra belt length to make that belt go above the entire earth all the way around. It still kind of amazes me. The other nice thing here is, if you really feel this well in your gut, you can do this problem quite quickly in your head without pencil and paper and a lot of rigmarole. But let me show you kind of the more traditional way of solving this problem, just to give you a comparison here. So the somewhat longer solution, we start with the same basic idea, same formula. The circumference of the earth is pi times bigger than the diameter. So it's pi times 7,901 miles. And the circumference of the earth, remember, is that distance around the equator. It's the distance of the smaller belt. And we want to compare that with the distance of the larger belt. And the length of the larger belt, we're going to use the same formula. It's pi times bigger than the new diameter. And the new diameter is not just the 7,901 miles. No, it's the 7,901 miles plus those extra 2 feet. The foot on the left, the foot on the right, like I showed you before. So it's pi times bigger than this whole quantity. And that's the same thing as being pi times bigger than this term plus pi times bigger than that term. It's the distributive property. So it's pi times bigger than 7,901 miles plus pi times bigger than the 2 feet. So what we want to do is we want to compare the length of the enlarged belt with the length of the snug belt. So we're going to subtract this length from this length, the length of the smaller belt from the length of the larger belt. So that is going to be this larger length, which is just taken from here, minus the smaller length, which is taken from up here. And the thing to notice here is we've got some really big numbers floating around, right? Pi times 7,901 miles. That's the circumference of the Earth. That's the distance around the equator. It's like 25,000 miles or something. It's way up there. It's really big. But the neat thing here is that this distance is exactly the same as this distance. So even though they're really big, they completely cancel out, right? This distance here on the left cancels out with this distance here on the right. And when we're done, all we're left with is the pi times 2 feet, which of course is equal to the 2 pi feet. Congratulations! You've made it! You've made it through all 4 parts of this pi video series. And I'm hoping that you now understand pi better than ever, and in ways that will be very easy to remember for years and years to come. I'm also hoping that you picked up some other math concepts along the way, and maybe you're even thinking about math in a different way than before. You know, the nice thing about math is that you can do it anywhere. You can do it if you're stuck in a long line at a store. You can do it if you're on a long trip on the car, if you're stuck in the car or on a bus. You can do it anywhere. And you don't even need to have a pencil and a paper and a book with you all the time. You can just think about it. In fact, I think that's part of the reason why mathematicians are often, so spacey. They have that reputation, right? And I think the reason may be that there's just so much cool stuff to be thinking about all the time. Alright, so this is Eric wishing you well and hoping that all of your math comes from the gut.